Welcome to the review of our exam review. Hopefully you've had a chance to work through the review on your own and you can get your solutions confirmed in this video. But first let's talk about the review itself and the exam. This review will be longer than most because it is the first exam and people are understandably nervous about that first exam. The exam is going to be in e-learning. It's a timed online test. You can start any time during a 24-hour period that the exam will be open. You'll have an hour and 15 minutes. The test will automatically close at the end of that. I'm going to use Honor Lock. There's just one attempt. The questions will be randomly drawn from pools of questions. They'll be presented one at a time without backtracking. If you get knocked out of the exam, you can usually get right back in. If not, you could contact me with this number. All right, let's look at the details. It's a 100-point exam, and the reference sheets will be accessible during the exam as a whitelisted URL, similar to the way I did for the practice exam. The exam has 33 questions, and what you'll notice is that the point value decreases as you go through the test. So you want to spend your most time on the first part of the test. If you finish, great. If you don't, then the last few questions are 2 points, so it won't hurt as much. And again, if you don't finish the exam, don't panic about that. What I'll do is look at the exam grades, look at how it impacted the overall course grades. And if it turns out that nobody finished, then obviously in that case I would have to curve the exam. But I anticipate that most people will finish, perhaps a few won't. So you should go through that practice quiz and practice using that whitelisted URL of the reference sheet so that you know how to manage that. And here are the settings that I have for Honor Lock. Honor Lock is a little bit sensitive to background noise. So if you have to take your exam in a relatively noisy place, Honor Lock may flag it, but they're not going to kick you out of the exam. So when they flag something, I go in and take a look at it and I can see that really it was nothing serious. If you have accommodations through the OSA, then you'll have your extra time added as long as I know about that. And I realize that the no backtracking option is extremely unpopular. People hate it, and I understand that. The reason I think it's important is partly for exam security reasons, but main reason that I do it is based on my experience with Honor Lock. There are a lot of students that have really bad Wi-Fi, and that's not their fault. It may be the Wi-Fi their dorm provides or the Wi-Fi that their family provides, and that's what they've got. If I allow backtracking, then that gives an inherent advantage of people who have great internet connections. And that's not what I'm trying to test here. So that's really the primary reason that I don't do backtracking. All right, let's look at the content of the review. Obviously, none of these questions will be on the exam. The point of these questions is to help you focus in on and understand what you already know well and what you might need to work on some more. So you could have a problem like this. You have a simple expression in C that you need to implement in MIPS. So I wish this were a live discussion so that you could point out any typos I have in here. I always have typos, but I can add those comments later to the video. So here we have variables. In MIPS, of course, we use registers. So I'm asking you here to use registers S1 through S4 for X, Y, Z, and Q. So when you have an expression like this, you have to break it down according to the order of operations. So there's no parentheses. We'll just do X plus Y first. So that's S1 plus S2. And since the result is going to be in X, and I'm only using X once, I can go ahead and put that here. Next we want to add Z. And finally subtract Q. So for these kind of problems, I generally look over your code and make sure that your code makes sense. You don't have to do this exactly the way I did it because there's maybe 20 different ways that people did it. So don't worry about doing it the right way or the one true way because it's coding. There is no one true way. All right, similar thing here. We have an if statement. If A is less than B, then we're going to replace C with B. Otherwise, we replace C with A. And here we're using registers T1 through T3 for ABC. So when we convert something like this, the first thing we do is do the opposite of the condition. So the opposite of less than is greater than or equal to. I chose to use the pseudo instruction. That's just one way to do it. So we're seeing if A is greater than or equal to B. In other words, this condition is not true. We'll jump down here to else, and we'll put A into C. You could use a move. I didn't add here. If this condition is false, we fall through and we put C equal to B. So B goes into C, and then we have to jump over the else. Here's a function. So I'm not asking you to write a complete program. I'm just asking you to implement the function code. And then I'm asking you to implement the code here below the comments that actually would call this function. So this function checks if n is 0. If that's the case, it returns 0. Otherwise, it's going to return n minus 1. So the first thing we do in the function is we put 0 in V0. We're using V0 as our quote-unquote return register. And that accounts for the base case that n is 0. So now we need to check, is n, which is going to be A0, and that's in our assumptions up here in the prompt. If A0 is 0, we can just return. We've already put 0 in V0. If that's not the case, we're going to fall through and subtract 1 from n, put that in V0, and then return. Again, many ways you could have written this. So the calling code is just jump and link, JAL func was the name of my function here. And then the prompt also asks you to store what was put in V0, store that in location result. And here I didn't follow my own directions. I wrote in instead of result. Okay, now I followed my own directions. So again, you're not going to be asked to write a whole program for time reasons. I'll just kind of hone in on what I want you to understand. All right, write instructions to push S0 on the stack. First thing we do is decrement the stack pointer by 4. -4, why is it negative? Because the stack grows up. And then we store what we want to push out there, which is S0, at the location pointed to by the stack pointer. Again, parentheses around a register mean that this is interpreted as an address. Pop, we do load word, so that will copy wherever the stack pointer is pointing, copy that word into S0, and then we have to adjust the stack pointer now by +4. In this next problem, we have a couple of small integers. We've got to convert those into binary, add the numbers. In the practice problem, I'm asking you to also convert it back to decimal. That won't be part of the exam question, but you might want to do it just to check yourself. And you have to show all the work. All right, to convert a number, decimal number, to binary, I admit this will be a little bit more challenging given that I won't allow you to use scratch paper. These will always be 8-bit numbers, so the place value is 1, 2, 4, 8, 16, 32, 64, 128. I won't have any numbers that big that you need to worry about 128, so I'll just put a dash there. And this place value is 64, so I'll put a 1 there. Mentally, if I subtract 64 from 67, I know that's 3, so I can put zeros in all these other places until I get to 3. So that's how you could kind of mentally convert a number since you don't have scratch paper. And then you'd always want to check it. So here I'm writing +67. That's 1, 2, 4, 8, 16, 32, 64. So 64 plus 2, 66, plus 1 is 67. And then you could convert that to the negative by copying right to left through the first one. So that's pretty quick. We got that right here. And then inverting all of the bits this way. It kind of helps me to have a space between the groups of 4 bits. It's not necessary, it just kind of helps me keep things straight. Next I have to convert 42. So again, this is 1, 2, 4, 8, 16, 32. So I put a 1 here for 32. Now I've got to come up with 10. Well, that could be 8 plus 2. All right, so now that I've got negative 67 and 42, I can add these. 1 and 0 is 1, 0 and 1 is 1, 1 and 0 is 1. 1 and 1 is 0 carrier 1. So now we'd have 1 plus a carry would be 0 carrier 1. 1 plus 1 plus the carry is 1 carrier 1. The carry of 1 plus 0, 0 is 1, and 1 and 0 is 1. So this is my answer right here. I hope that that's negative 25, because if I add these in decimal, I get negative 25, so I can check that. I copy my answer here, and then I'm going to convert it to positive, again by copying right to left through the first one, and then inverting all the bits. And now that I see that I've converted it, I notice that it's 25, so that gives me confidence in my answer up here. This check part I'm not going to ask you for on the exam. And on all of the exam questions of this type, your answer is going to be positive anyway. I always make the negative number smaller than the positive number so that you don't have to go through this wondering what the heck that number is. All right, these 2 questions, we want to set certain bits to be 1, and how do we do that? So specifically, we want to force bits 5 and 7 of T0 to be 1 and leave all other bits unchanged. So the answer here is hex, so I write hex 0x, and the answer is A0. How'd I get that? Well, first I numbered my bits. Bits are always numbered right to left, starting at 0. And we said that we wanted bits 5 and 7 to be 1. So I'll make those 1 and leave all the other bits at 0. And when this is ORed with any number, it will leave all of the bits where there's a 0, leave those unchanged, because when you OR with 0, it's, nothing changed. And it will force whatever it was at bit 5 and 7, it will ensure that those will be 1, because when you OR with 1, the result is a 1. So this is binary 1010, 0000. If I write that in hex, group these in bits of 4, I've got 0000, which of course is 0 in hex, and I've got 1010, which is A in hex. Now we're kind of doing the opposite. We're forcing bits 5 and 3 this time to be 0. Again, I wrote my bits out here, and I want bit 5 to be 0 and 3 to be 0, so I put zeros there and make everything else 1. And then again, grouping those in groups of 4. This is D and this is 7. So remember that we want to leave all other bits unchanged. That means all the other bits. There are 32 bits. So that means I need 1 every place except these 2 locations. How can I do that? I can write it like this. So F, 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 F. Each of these is 4 1s. So that will ensure I've got all 1s and then D7. So why didn't I have to put leading zeros here? Well, you don't have to put leading zeros because it'll be 0 by default. If I leave out these F's, then I would have zeros here, and it would force all of the bits from 8 to 31, the most significant bit, it would force all those to be 0, which is not what we want. So that's why I had to put those F's in here. All right, moving on. What does this code do? Well, it adds T0 to itself. That effectively doubles it, multiplies it by 2. If we wanted, nice thunderstorm here. If we wanted to use SLL instead, that would be shifting left logical 1 time, because every time you shift left logical 1 place, that's the same as multiplying by 2. All right, we want to implement a loop here. And again, I'm not going to ask you to write anything this long. This is actually a complete program. But this will just kind of help you refresh your memory on array indexing. So let's say we have something like an array, and of course we don't really have an array in assembly language. We don't have any data structures, but we can have multiple items at one address. So effectively this acts a little bit like an array. This is pretty much from the book. So I'm going to load the address of that array into S6, and I'm going to make S3, let that be I, and start it off at 0. And here's the loop. First time through the loop, we're shift left logical twice, which multiplies I by 4. Well, I is 0, so multiplying it by 4, it's still going to be 0. So T1 will be 0 the first time through. We add that to the base address of the array, and so now T2 is going to point to the first array element. It'll point to this 1 here. Here's the body of the loop. It loads that element, adds 3 to it, and stores it back out there. Then we need to add 1 to I, check if we're done, and loop back up. Next time through the loop, S3 has a 1 in it, and when we multiply 1 times 4 with the shift left logical, now it's 4, and when we add that to the base address of the array, second time through the loop, T2 will be pointing here. So again, you won't be writing anything this long, but it's important to go through your homework and the book sample code to make sure you understand code. For each addressing mode, write a sample instruction using that mode. You won't have anything this long. I will more ask you, I'll give you, let's say, an instruction, and it will be multiple choice. Tell me which addressing mode it is. Or I may give you an addressing mode with maybe 4 different multiple choice options. Which one is that addressing mode? So you kind of need to memorize this, but it's going to be multiple choice, so it's not that bad. Register addressing mode is when all 3 operands are registers. Immediate addressing mode is when the third operand is a constant, an immediate value. Base or indexing addressing mode is where we're using an address. Typically like this, we're using a register to hold an address. PC relative is for branches, and pseudo direct is for jumps. So don't confuse the 5 addressing modes with the 3 instruction types. So remember that the R format, the R instruction type, is always associated with register addressing mode. The J format is always with pseudo direct for a jump. And all of these 3 addressing modes use the I instruction format. Alright, we're on the last page of the review. If you have a problem like this, where you start off with the hex and we want to know what MIP statement this is, don't just write the statement. I want you to show enough that I realize how you worked it out. You don't have to write this much. I'm kind of over-explaining here for the purpose of this video. First thing you do is take all of these hex digits and expand them into binary. And then you want to regroup them. We know that the first 6 bits are always going to be the opcode. Once I see that the opcode is all zeros, I know that it's an R instruction format, which means the last 6 bits are going to be the function code. And I know that we're going to have 3 groups of 5 bits for RS, RT, RD, and I'm going to ignore this shift amount. So what we see now is that my opcode is 0, and my function code is 22 in hex. So don't try to convert this. 10 is a 2, and 0010 is another 2. That's a subtract. So you can look that up on the reference sheet and see that it's a sub. Next we need to convert these registers. So this is 9, which I know is T1 because I memorized that T0 is 8. And this is 11. And if 9 is T1, then 11 must be T3. And this is 16, and I've memorized that that's S0. So now I just have to put the registers in place. And remember that in RD, even though it's in the 3rd position in the binary, when we write it, it's first. So we have RD, RS, and RT. This problem, we're going in the opposite direction. We'll look up or opcode function code 0/25, and we can convert all of these registers to their binary equivalent. And then we can just put everything in place. Here's my 6 bits for my opcode. Here's my 6 bits for my function code, 2, 5. And then here is my RS, my RT, my RD, and I have to leave 5 zeros for the shift amount. And then I regroup those. This answer is correct in terms of the binary, but I'll need to see the hex as well. So it's just a matter of regrouping them and getting the hex digits. This problem asks you to convert another expression, and it tells you which registers to use. So we're going to follow order of operations and do parentheses first. It asks you to use mult. So mult takes 2 source operands. The result will be in the high-low registers. We're going to assume that it was less than 32 bits, so we're only interested in the low register. So I'll copy the product of T2 times T3. I'll copy that into just some other register I'm not using, like T5. Now I need to do 10 times A. So I'm going to put 10 into another temporary with load immediate, and then mult. And again, I'll move that product into some other temporary register I'm not using. Then I'll have these 2 intermediate values, which I put in T6 and T4. And I'll subtract them and put the result in T3, which is C. Further advice is to review your homework, make sure you understand it. Review terminology from that first section of the first chapter, first 5 sections. And look through the practice problems on control structures in the GitHub. And don't forget to practice with the practice HonorLock exam, opening up these reference sheets. And by the way, I will post this annotated review in Piazza.